Okay.
So a frequent task in rendering is to evaluate integrals of radiometric quantities. So these chapters just talk about those stuff. I appreciate that they spent a section just talk about this. We will take the computation of irradiance at a point as an example. Yeah, we often need irradiance when we do some kind of baking kind of stuff.
Ye-
So irradiance at point P with a surface normal n due to radiance over a set of direction. What's
Omega.
this? Omega.
You can hover over it with the mouse cursor and it will tell you
Oh,
because
cool.
it's all LaTeX. So
It's actually really useful.
yeah, I found that out last week when I was like, what the heck is this? Oh, it's blah.
I seriously should put Greek letters into flashcard.
Street cred in the graphics programming crew.
Yeah. And yeah, so we have this integral, which is radians, incident radians from a point and angle, a cosine term. And data mentions the angle between the omega and also the surface normal. Yeah. Usually computed over hemisphere. So that's why we often have divide by 2 pi problem, not 4 pi. In
So
this,
if I'm reading this right, this hemisphere is the integral of all of the radiance coming in to point P as, all the incident radiance. Or is that
yeah,
referring to radiance like okay, I'm thinking of something else, never mind.
yeah, just the irradiance. The radiance is irradiance per solid angle. So irradiance is like we need to integrate back from from some a certain
Yeah. Yeah, the figure 4.a, irradiance at point P is the integral of irradiance times cosine of incident direction.
Yeah.
So it's kind of taking out the hemisphere. It's over the entire hemisphere, so it's effectively removing the incoming direction in just all directions.
Yeah.
Okay. I think it was confusing me because it said radiance and it could have been the, radiant excitance or excitant radiance, which is different.
So, which is just yeah, But I think the book said like people just call it irradiance. A lot of people.
Yeah, they definitely there's a lot of confusing terminology or loose terminology.
It's just extent is the outgoing radiance.
Yeah.
So projected solid angle. Because the cosine factors can be distracting. So the problem can be avoided using projected solid angle. So instead of integrate over the solid angle, we integrate over its projection into a sphere. No, not sphere, into a circle. Yeah, shape down into unit disk that's perpendicular to the surface normal.
I think this illustration makes it clear that the solid angle is an area. It's
Yeah,
just you can just it's around a not a flat plane or a it's not it's an area in non-Euclidean space. Is a sphere non-Euclidean?
It is Euclidean, I'm pretty sure.
Oh.
yeah,
Uh,
I don't know what non-Euclidean geometry is talking about, but
well, it's the okay,
seem
I'm
to involve some hyperbolic stuff. So
It's like, yeah, like curved. Like if you have a triangle on that sphere, if you draw a triangle on that sphere, and so that triangle could have angles greater or less than pi. So that's non-Euclidean. Um, do you know what I'm saying?
yeah.
I do, but I also am wondering if I'm confusing terminology that should not be used in this context. With, non-Euclidean meaning something rather specific, and I don't actually know what that means, and it's not really relevant to what we're discussing. I'm like thinking about how the sphere it's a 2D space, and you can if you project it down onto a circle, that's totally fine.
Yeah. I don't understand how by projecting down, it's okay that you can just use that disk to
Well, it's
calculate.
equivalent. It's not that it's not okay to use the hemisphere. It's just the cosine is distracting. It makes it kind of seem like there's magic going on, magic values. That's my opinion.
Huh.
Yeah, it's equivalent, but well, cosine still exists. It's just hide in the differential now.
Yeah. So what's the upside down T called on the D delta omega or the D omega?
Perpendicular.
It is perpendicular, yeah.
Oh, it is.
It's actually a useful, intuitive symbol for once.
Yeah. What's the onomatopoetic equivalent for math terms that look like what they are?
Interesting question.
Well, for the rest of the book, we will still use integrals in terms of solid angle, so not this. Yeah, I guess this notation is just not that common. But yeah, it may be used, and when it is used, you need to aware what's the integrand actual measure.
Yeah, just I Googled and found this, and it seems like a good answer to our question for later, rather than
Yep.
getting into it right now.
Integrals over spherical coordinates. So we can transform integrals over solid angle into integrals over spherical coordinates. Theta phi using equation 3.7. I assume it's just, yeah, it's just like spherical coordinates. So in order to convert integral over solid angle to integral over those two variables, we need to express the relationship between the differential. The differential area on the unit sphere is the product of the differential lengths of its side mm, sine. I'm a bit confused about where does this comes from.
Yeah, because what is that? Phi is on the disk.
Yeah,
So
phi is the, yeah,
so
I
the
understand this term, right? For the sine, oh, sine theta is like the projection from the normal. No,
Oh,
yeah, from this vector into the normal.
it's the same. It's doing the same thing as the projected area of above, rather than the multi-dimensional approach that I was assuming would be done.
Yeah. And this result can also be derived using the multidimensional approach. So yeah, you are ahead. Yeah, I'd rather not dealing with Jacobian matrix if I don't need to. So differential area d omega subtend by differential solid angle. This is just this. So for irradiance integral over hemisphere, we can extend it to this, which we already have a cosine term. Now we also have a sine term now. But the good thing is we don't need to integrate over a hemisphere. Instead, it's just become one-dimensional integral. I had a calculus professor who insists us to always write what variable it is when writing the integral sign, and I agree. Like, this just looks confusing. Integrals over area, so irradiance again. Imagine we have a quadrilateral with constant outgoing irradiance, and we want to compute that. Compute this value as integral over direction omega or spherical coordinate is not straightforward. So since it is non-trivial to determine if the quadrilateral is visible in the direction. So it's easier to compute irradiance directly as integral over this area. Differential area dA on a surface is related to differential solid angle as viewed from point P by this. Let me read the below first because I don't understand what's going on. Theta is the angle between the surface normal and the vector P. So the cosine term is to project from the normal to the view direction, I assume. And R is the distance from P to dA. That makes sense. And oh, is this just inverse, like square? What that's called, inverse square law or something for the light force rule?
Yeah.
Yes, you're right.
Yeah. Yeah, just intuitively, we have this, like when the area move away, we have force rule followed by square, and then if the like outgoing radiance direction is not aligned with normal, we also have a force rule, which is in the cosine term. So yeah, therefore we can write irradiance integral for the quadrilateral source as this monster. But yeah,
I can see why having the equation formula for a quadrilateral light source would be useful because, as it turns out, you can express a lot of shapes using a bunch of individual quadrilaterals.
yeah.
Wonder if the math is harder with trying a triangular area because it doesn't have the nice square that you can just reduce down by 2 dimensions when you do the integration across it.
Yeah, I guess for this part it's still the same. This part mentioned no quadrilateral at all. It's the difference is how we integrate that become more difficult.
I see.
Yeah, we have a theta I, which is the angle at here, and we have a theta O, which is angle at here. I think we're done with this chapter.
Shorter than I thought, but also rather complicated stuff.
It's short. So